since we've done problems that involve, component work or extensive component work. So let's look at one kind of like number 17 in our book. It says we have a ball with a mass of 0.600 kilograms is initially at rest. It is struck by a second ball having a mass of 0.400 kilograms, initially moving with a velocity of 0.250 meters per second towards the right along the x-axis. After the collision, the 0.4 kilogram ball has a velocity of 0.200 at an angle 36.9 degrees above the x-axis in the first quadrant. Both balls move on a frictionless horizontal surface. What's the magnitude direction of the velocity of the 0.600 kilogram ball after the collision? So that's what we're looking at. So we're going to have this collision, and it's described in terms of an XY coordinate system. Okay. Now, one of the things that's a little odd about this description is that they go in and they describe the one that's at rest to begin with, and then the other one moving towards it. So we're kind of moving in a funny direction, I guess. So we'll put this will be our second object, and this will be the first object. So I'll do M1, and this one is M2. So left and right, 1 and 2, but they described it as this one first and that one second. So, funniness. They said that the first one was the 0.6. Yeah, 0.6 kilograms initially at rest. So 0.600 kilograms. And then our V2 is 0. And then the second one was the 0.4 kilograms. And it's initially moving at 0.250 along the x-axis. 250, like this. Okay, there we go. And then there's the collision. I always draw my little squiggly line. I don't know. To me, that illustrates the collision. This is going to be our plus x direction. This will be plus y direction. So, and then it says the 0.4 kilogram was at 0.2, 36.9 in quadrant 1. So they're going to hit and then spray off. So then this is 0.400 kilograms. This is V1 prime. 0.2 meters per second. Let me trim that. Where'd my... Oh, there it is. Go. And this was at an angle of, I think it was 36.9 is what they were telling me. Quadrant 1. Now, this is where it'll get interesting, and part of it does depend upon how we want to code things in. But essentially, if the one goes up, then the other one should go down so that we conserve momentum, right? Because if one of them has a momentum in the positive y, and we had no y momentum to begin with because it was purely moving in the x, then the other one has to end up going kind of down in this quadrant 4. So let me put that one here. So this is M2 is our 0.600 kilograms. And then we're going to have this unknown V2 prime. And it's going to be at some unknown angle, okay? And so then this is going to illustrate one of the things that we want to talk about. So we have these two are the unknowns, the magnitude and the angle for the direction. But we really do not want those as our unknowns. Okay, we would much prefer to have the x and y components of those be our unknowns, because otherwise you're going to have this unknown angle inside either sine functions or cosine functions to work components. And then you end up with trig equations, which isn't horrible, but I mean, it's kind of like tying your shoestrings together and then going to run the marathon. I mean, it just makes it harder than it needs to be, and for no really good reason. So we are going to go in. So this is our question, and what we want is this, after collision velocity on this second object is what we're looking for. And so then what we're going to do is we're going to go in and find our, components. So if we come in here, then what we'll get is that our, V1x component is plus 0.250 meters per second, because positive x is this way. And we're going to note that our V1y component is 0. So the x and y components for 2 are both 0 because V2 was 0. Then we will need to go in and calculate the x and y components of this V1 prime. Okay, so this will be V1 prime, the x component. And then this one up here will be V1 prime, the y component. Since this one's opposite the 36.9, then it's the sign. Okay, so it'll be the 0.200 sine 36.9 degrees. And we'll need to decide if we want to put in the directions now or if we want to put them in later when we load the equations. And it doesn't matter how we do it, as long as one, we do it, and two, we don't do it twice. So, you just want to be a little careful. I think I'm looking at it right now. We'll put in that it's going to be positive. And let's calculate that for me, please. And then the x one's adjacent, so it's going to be the cosine. So 0.200. Notice it goes in the positive x, so this one will be plus as well. So let's find those, please. Thank you, Olivia. 120 for the y, and the x is 0.160. And so at this stage, I don't want to do an unknown magnitude times the sine and cosine of an unknown angle. We want to avoid unknown angles inside trig functions if at all possible. So I'd rather run it as an unknown x and an unknown y. Once I solve for these two, I can do an inverse tangent to get the angle, and I can do a Pythagorean theorem to get the magnitude. And so that's how we're going to, proceed from this particular point. Now, what we can note is we can go in and note that the net average force over the system in the horizontal direction is going to be 0. Okay. And this is because ball 1 will exert a forward force on ball 2. Ball 2 will exert a backwards force on ball 1. There will be some components to those, but really 1 acts on 2, 2 acts on 1. So by the third law, those are going to sum to 0. And then you have gravity is down, normal is up, and it was frictionless. And so vertically, we would be in equilibrium there as well. But there's no motion of the ball, up off the table. There's no motion of the ball down into the table. So I don't care about the vertical direction at all. And so this is essentially by, Newton's third law, which is good because I can't tell you how much force 1 acted on 2, but yeah, so there we go. And so then we have conservation of momentum in both the x and the y directions. Okay, in either the horizontal type of direction, so both x and y. So let's go in and let's take a look at this. So Yeah, I think I do one and I'll have to go to the other page. Conservation of linear momentum. In the x direction. And so then what we get here is this is going to be our m1 v1x plus our m2 v2x is equal to m1 v1 prime x plus our m2 v2 prime x. And I'm going to drop the vectors kind of like we did back in chapters 3 and 4. I know they're vectors. I'll put in my directions. It'll be fine. Just makes it a little easier to write, I guess. So I could keep them if you want. I guess it doesn't matter. But for our mass 1, this is 0.400, and then the x component of this velocity is the plus 0.250. For object 2, it was at rest, so that's a 0. And then this will be our 0.400, and then the x component of v1 prime is that, plus 0.160, and this will be plus 0.600 times this v2x prime. Now I'm going to go in and say that I know that it's going to go in the positive direction, v2x prime. And so here's my direction, here's my magnitude, and then it's the only unknown in the formula. So we're going to solve and get an answer. And so we'll move this term to the other side, and then we'll divide everything by the, 6. And I'm going to flip the formula because I'm annoying like that. And so this will be 0.400 times 0.250. And then when we move this over, it'll be minus 0.400 times 0.160. Like this. And so then what do we get for our x component of the velocity of the second ball after the collision? No, it does not. I'm using primes to indicate before versus after. So the notation, so it's not a derivative notation, because we wouldn't know derivatives, right? But yeah, I use the primes to be final and no primes to be initial to remove subscripts, because otherwise we would have a 1x initial, a 2x initial, a 1x final, a 2x final kind of things, and then you end up with like 3 subscripts. And so I'm trying to minimize how many subscripts we have on each term that we write, because I usually find that once we hit about 3 or so, I'm not real happy with the notation then. So then it's probably in our best interest to adjust it. Yes. So thank y'all. 0.060. And I'm seeing 3 digits, so I'll put another 0 on there. There we go. It came out positive. So the direction we picked, and I picked my direction here, this would be, in the positive x direction, or to the right. And so since this is positive for the magnitude, then it is indeed to the right. Okay. And so then this was in the x direction. And then let's go in and take a look at conservation. And the y direction. Okay. And so we'll do, this is m1 b1y plus m2 b2y. And I could put the extra lines on there, but I guess I'm not going to. m1 b1 prime y plus our m2 v2 prime y. So before and after. And object 1, object 2, object 1, object 2. These are all y components. And what you'll notice is that since this was moving purely along the x-axis, the initial y component for object 1 is 0. And since the second object was at rest, then its y component is also 0. And so this is our 0.400 kilograms. And then the y component going up like this is going to be our positive 0.120. And then mass 2 is 0.600. And then to balance the fact that one went up, this one must go down to conserve momentum is kind of how that goes. And so this will be a minus V2 prime Y. Okay, so that's this component there. And so then once we have this, then what we can do is we can move this term to that side. So first off, that'll make it positive, and I'll put my, unknown on the side I like to see it. I like them on the left. So 0.600 times our V2 prime Y equals this 0.400 times 0.120. And then to solve, we just divide by the 0.600. And we get that V2 prime Y equals what? So if I make it into the vector, this would be, to the right. So 0.0800, I guess, or 3 digits. And now notice that my magnitude was positive. So what that means is the direction we picked was correct. And when we loaded this, since we loaded this y direction as negative, then we're going to call it down, It's down on the page, not vertically down. So, there we go. And so getting a positive answer for the magnitude means this direction was correct. And so then it's this speed. So if we make this our vector, then it's going to be, down on the page. Be more clear. Okay. So now we have the x and y components of the second ball after collision velocity. So we can find our magnitude and our direction. And so we're almost there. And so then let's go in and let's find V2 prime, this magnitude. So that's the x magnitude, so the 0.06 squared, and then the y, 0.08 quantity squared, gives us what? I think it's 0.1. This is 345. And they get our angle. They call it theta 2 prime. Yeah, I did call it theta 2 prime. I'm going to do the inverse tangent. I'm going to do the y over the x. I'm just going to do magnitudes. So the y1 was the 0.08. The x1 was the 0.06. So this is like the 51.3. Is that the one that was for 345? I think it's 51.3 for 345. But it's actually calculated because I mark it back easily. 51, 53.1. Oh, I said it wrong, didn't I? Like I said, it's a good thing we calculated it. All right, so then we put these together. Now, the way you report the direction, we have the angles. You're going to give it the same way they gave this angle for the V1 prime. And what they said was that it was at an angle of 36.9 degrees above the x-axis in the first quadrant. So then we would be below the x-axis in the fourth quadrant. And I would always say it's the positive x-axis, but that's just me. So we look at our V2 prime, the magnitude is 0.100 meters per second at our angle of our 53.1, not 51.3. This would be, below, and I would go with the plus x-axis in quadrant 4. So we'll kind of add my plus in there that I like, but they didn't do that, but we'll be all right. And there we go. How'd we do?